Hi guys, how's it going? My name is Nick Schneider. I'm going to be taking you through logistic regression, a machine learning technique. It's not going to be super in depth. It's going to be a little high level, but I want to try and talk about each piece, hopefully get a deeper understanding of it. And let's start out by saying logistic regression is actually a statistical analysis. And we're going to be taking a quick look at linear regression, which is also a statistical analysis, but a more simpler form of it in a sense. So the basics of regression, or the goal of regression, is to find the best fitting line for a set of points. Now, you look at this graph, it's just a normal graph. We have the dependent variable y right here. We have the independent variable x right here. We have this line of an equation right here. Don't worry about this lower equation yet. We'll just have a few words on it in a second. So the goal of regression is to find the best fitting line for all of these points right here. Notice these points aren't in a straight line, so there's a bit of an estimate, there's a bit of a fitment for this line, but in the end, the distance between each point in the line is balanced out. So on either side of the line, the distance is somewhat equal, somewhat balanced. That line's pretty much right in the middle of all those points. And I'm gonna kind of go over the process that it takes to get to that and how logistic regression is dissimilar from linear regression, but similar in the same sense. So let's look at this bottom equation again really quick. This bottom equation, I just threw it down there really quick just to show you that regression isn't just a simple y equals mx plus b line. It can have more variables, and also in machine learning they don't call them variables, they're called features. So it can have more features. So you can have right here b0 actually correlates to the x-intercept, b1 x1 is mx plus b. You can have b2 x2, b3 x3, and the b's also, they're not called b's, they're weights. So in machine learning, we're actually trying to optimize each one of these b's. And these b's actually place this line that certain distance from each one of these points x. And then you'll get that y. And so each one of these weights, once they're learned, we have the line, we have the equation, these weights are learned, you can then take new data, new points, new dots, put their features into this space right here, into these x's, and spit out a new y, and that y is going to predict where that's going to fall from this past data right here, all these blue dots. So that's how machine learning kind of works. You use a bunch of past information, a bunch of past data, you put it into a graph, you find a line, the equation of a line that best fits all that data, and then you can put in new data to predict what's going to happen next. So let's move on to logistic regression. Logistic regression is actually a classification problem, unlike linear regression, but we're still going to use the same process that linear regression uses to build a model, but in a little bit of a different way. So being a classification problem, that means you have, say, a medical condition, or you don't have a medical condition. So you go to the doctor, you get a bunch of tests done, they look at the blood sample in a few different ways, they find out from the blood sample that you have the condition, the probability of that condition is going to be 1, or the probability of that condition is going to be 0. We use a function called the sigmoid function to actually map these points from 0 to infinity into this space from 0 to 1. And right here, the actual equations for the sigmoid function. Here's the graph of what the sigmoid function looks like. It's an S-curve. And the sigmoid, and being probabilities, we're going to need to be able to judge. So say you have like some points in the 7 area, some points in the 3 area. What do? You make a decision boundary. You have a decision boundary. So this decision boundary splits up the points between the 1 area and the 0 area. Not everything's going to fall on the 0 line. Not everything's going to fall on the 1 line. So you have to have a statement in however you're doing this saying if the x falls on the 0.5 range or higher, it's going to equal 1. If the x falls under that area, it's going to equal 0. It's called the decision boundary. I just wanted to point that out to everyone. Normally it's set at 0.5. You can change it depending on your model, but most of the time 0.5 is pretty sufficient. We're going to move on. Next, we have this thing called the cost function. The cost function is actually the cross entropy function. And they use the cross entropy function for logistic regression because of the logs that it uses. These logs kind of, since it's not a straight logistic regression, if you go back to the sigmoid function, it's an S-curve. It's not a straight line like linear regression. So they need a function that actually works better with the curve. And this function, since it uses logs, it works with the curve. Now, notice it's split up into two portions right here. If y is 1, you use this cost function. If y is 0, you use this cost function. Now, we need to combine those, and there's actually right here a sneaky trick to do that. You multiply the top one by y and the bottom one by 1 minus y. And in the end, right here, this is what the combination of both of those look like. So when you get y equals 1 right here, that correlates with this one right here. That means this will be 1. You come over here, look at that. 1 minus 1 is 0. That cancels itself out. So you don't even use that one when y is 1. Now when y is 0, you plug in 0 here. That one cancels out. You plug in 0 here. That's 1 log times 1 is 1. This one is used. So sneaky little great trick, but this cost function, it's definitely going to come into play more in the end. But here's a quick little brief description of the cost function. This cost function is the idea that you have this dot right here and you have a line right here. And say you have dots all over the place on this graph. You can't see them right now, but this is like the best fitted line. The cost function gives you the cost that it takes to get from this dot to this line. This distance right here is the cost function. That's what that describes. So we are going to want to minimize that distance. And how are we going to do that? With the gradient descent. Now, when I got into machine learning, I was very confused on gradient descent. I wasn't exactly sure what gradient descent was. I thought it was an equation. When in a way it is an equation, but it's not. It's actually more of a process, an algorithm, an iterative process of finding the minimum of a function with first order derivatives. Now, if you look at this cool little image right here, you'll see this red line is the derivative of a function. And then the gradient descent would be these x's and these arrows. And what gradient descent does is it iteratively goes taking steps down, 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 like you're hiking almost, until you get to the bottom. And when it gets to the bottom, it'll know it's there, it stops. And then it returns that you found the minimum of the function. Now, what that means is you go back to that dot with that line, and for the cost function, let's go back really quick. This cost function, that's going to be the minimum distance from this dot to this line that can possibly happen with all these other dots over here. So if you move this line this way too much, it's getting too far from this red dot and too closer to the dots over here. If you move this line this way, it's getting too far from these dots over here and too close to this red dot here. So you want all your weights to be as minimum and optimized as possible, which reach right here. Now, one way of doing this also with the gradient descent, which it's used all the time in machine learning, is this idea of alpha. Alpha also known as the learning rate. What alpha does is it multiplies the gradient by the amount of step you're taking. So you can shrink your steps, make you take more steps, or you can grow your steps. Alpha just says it helps you with finding a good step. But with finding too big of a step, you could jump over the minimum and you'll never find it. Or with taking it too small of a step, you take 2 small steps, you'll never really reach the minimum. You'll never find that bottom part of that gradient. So you always need to make sure you have a good alpha, good learning rate. Now, with this next equation, I'm hoping to kind of start tying this all together for you guys. This equation let's not look at the theta j, the equals, the theta j, or the minus alpha. Let's just look at everything past the summation. This little area right here. Let's see if it'll let me highlight it. It will not. Well, you have h theta x minus yi xij. That is the actual derivative of the cost function. I've already taken the time to take the derivative of the cost function. You guys can try it on your own if you want, but that is the derivative of the cost function. Now, if you have that cost function and you multiply, so you figure out what that cost is from that red dot to that line, and you minus it from the original cost, you're going to get a new cost. And that's what is kind of happening here. So you have the cost. Well, theta actually represents all those weights, those b's I was showing you, the m and the b. And right here's the alpha, which you multiply by the derivative, that step that you're taking, which is right here. So think of an iterative process that starts you with an initial weight, and then you take a step away from the weight, you multiply it by alpha, and you minus it from those weights, and then you get a new weight. And then you check that new weight. You test that new weight to see how that new weight fits, to see if it's at its minimum. If it's not, you keep going. You take the next step. And then you take the next step, and you take the next step. Now, if you look over here, the h sub theta of x is actually equal to the sigmoid function. That's where the sigmoid function falls into this. So it's just a process of function to function to function kind of thing, where you put in your data in the sigmoid function, and then you put it into the gradient, or you put it into cost function. You start the gradient descent, you multiply by alpha to get the step, you take away from the weights, and you slowly optimize the weights. And like I said, once you have that optimized set of weights, and then you have the equation for that optimized line, you can then use it to predict new things right here. This is a project that I did a year ago, but this was the ending graph for it. I have all the zeros down here, I have all the ones up here, and here was the sigmoid that I've learned. If you guys have any other questions, you can get with me and I can hopefully give you a deeper understanding of it, but I hope this helps you kind of understand logistical regression a little more. Thank you guys.